Now let us come to this theorem. The set of all cosets of a normal subgroup H of a group G is a group with respect to multiplication of cosets as composition. So that means the set which contain all those left or right cosets of H will form a group under the binary operation, that is multiplication of coset as composition. So now let me take this G by H. Let G by H contain all those left or right cosets. In this case, without loss of generality, I'll consider the case of set of right cosets. That means G by H contain this set of right cosets Hx such that X belong to G. Or G by H also can be of this form. It contains the set of all left coset Xh such that X belong to G. Now what I need to prove is that this G by H forms a group under the multiplication of cosets as composition. That is G by H, the algebraic structure G by H under the binary operation multiplication of cosets as composition satisfy the group axioms. Here you have to note down this H should be a normal subgroup of G. Now first of all, to prove this one, let me consider this G by H is equal to this one. So let me take any two elements of G by H. Then the elements of G by H must be of the form HA, HB belongs to G by H, where A and B are elements of G. I need to show that HA into HB also belong to G by H. So how to prove this one? HA into HB can be written as HA, you can remove the bracket, it will be HA, HB. Now here, AH can be written by HA into B. Why? Because HA is same as AH if H is a normal subgroup of G. So that's why this normality condition is very much important, because you cannot prove the closure property or other axioms of a group until and unless H is a normal subgroup. Because if H is a normal subgroup, by the first theorem, HA should be the same as AH. So you can replace AH by HA. And what is HH? HH is same as H for a group. So this will be HAB. And this HAB still belong to G by H, because it is of the form HX, such that because AB belongs to G, it implies that A into B also belong to G. So it is of the form HX, which is an element of the form of that belongs to G by H. So therefore, it satisfies the closure property, which means that the multiplication of cosets as composition is a binary operation in G by H. Now next, let us prove the other axioms. The first axioms of a group is associativity. So take any three elements of G by H and let us show that HA into HB into HC. This is equal to what? It will be HA HB into HC. It is equal to H. Again here AH can be replaced by HA, because H is a normal subgroup. HA is same as AH. So into B into HC. And this is equal to HHAB into HC. HH is equal to H only, because H is a subgroup. So H into H will be itself AB into HC. So this is called to HAB HC. Again here AB into H will be same as HABC. So it will be HHABC, which is equal to HABC. Now here let me show you that what is HA into HB into HC. So this is equal to HA, then HB HC. And this is equal to HA into, now BH can be written as HB. So it will be HHBC. Again, this is possible because BH is same as HB, as H is a normal subgroup of G. So this gives you HA. HH will be same as HBC. Now AH can be replaced by HH by HA, so it will be HABC, because HA is same as AH, as H is a normal subgroup of G. So finally this will become H, again H into H will be H, so it will be HABC. So if you take this as equation 1 and this as equation 2, then we can conclude that HAHB into HC, this is same as HA into HB into HC. So that means it satisfied associative property. Now existence of identity element in G by H. We know that E is an identity element in a group G. So HE will be same as H, because if you multiply E with a subgroup H, then it will give you H only. And then we will show that this one acts as the identity element. Now we take, let HA belongs to G by H. Now let us show that HA into HE, which is equal to H, acts as the identity element. Now HA into HE, this is equal to HA-HE, which is equal to H-HAE. Why? Because AH is same as HA, as H is a normal subgroup of G. So this is equal to HAE. And what is A into E? A is an element of G. So A into E will be A only. So it becomes HA, as E is the identity element. So you see that HA belong to G by H implies that HA into HE is equal to HA. Then this implies that HE, which is equal to H itself, act as the identity element of G by H. Now next, the existence of inverse element for every element in G by H. So let us take HA belongs to G by H be an arbitrary element, where A is an element of G. Now as we know that G is a group, so if A belongs to G, it implies the inverse of A, that is A inverse, also belongs to G. So which means that HA inverse also will be an element of G by H, as G by H contain all these elements of the form HX such that X belongs to G. So we have HA inverse belong to G by H. Now I need to show that this one acts as the inverse of HA. So HA into HA inverse. This is equal to HA inverse. Again, AH can be replaced as HA, as AH is same as HA, as H is a normal subgroup of G. So this will be HA inverse. AA inverse gives you E the identity, so it will be, and HH is equal to H, so it will be HE, which is equal to H. So you can see from here that HA inverse now into HA gives you H, the identity element in G by H. So which means that the inverse of HA, that is the whole inverse, is equal to HA inverse. So every element of HA has an inverse in G by H. So this, from all these axioms, we are able now to conclude that G by H under the composition, under the binary operation multiplication of coset as composition, this one is a group because it satisfies all the group axioms. Now there are some important remarks. Number one is, if G is an abelian group, then the quotient group G by H is abelian. Note that this set G by H, or the set of which contain all the left or the right cosets of G by H, is called as the quotient group. So now if G is an abelian group, then the quotient group G by H also will be an abelian. So you can see the proof. For example, HA into HB will be the same as HB into HA. So it will be HA HB, which will be the same as HHAB, because AH can be replaced by HA. And what is this? It will be HAB. And what is HAB? It is same as HBA, because A and B are elements of G, and G is abelian, so AB is same as BA. So then you can write it again as HH into BA, because HH is same as H, so it will be HB into HA. So that means HA into HB is equal to HB into HA, which means that G is an abelian group. Similarly, if G is a cyclic group, then G by H will be cyclic. So that means there will exist a generator of elements of G by H. And the generator of this one will be, that means G by H will contain an elements of this form, HA to the power n, where A belongs to G. Okay, so you can show that every elements of G by H can be expressed as an integral power of HA. So therefore G will be cyclic. However, the converse is not true. That is, if G by H is cyclic, then G by H need not be, or then G need not be. G need not be cyclic. And the example for this one is, you take G to be S3, the symmetric group, And then we know that this contain I 1 2 1 2 3 1 2 1 3 first, then 2 3 1 2 3 and 1 3 2. We know that this one is not abelian. We have discussed this thing in detail. This is not abelian. If I take a subgroup of S3 which contains I, then 1 2 3 and 1 3 2. This one is a normal subgroup of S3. Okay, so therefore we can form the quotient group S3 by H, because a quotient group can be formed only, G by H can be formed only if H is a normal subgroup. So H is a normal subgroup of S3 which contain these elements. So this one S3 by H will be a quotient group. Now, why this one is S3 by H is abelian in this case? What is the order of S3 by H? Order of S3 by H is same as order of S3 divided by order of H. Order of H, S3 is equal to 6 and order of H is equal to 3 because it contains 3 elements. So this is 2. Now which means that order of S3, the quotient group by H, is 2, which is a prime number. And we know that a group of prime order is always cyclic. So by that theorem that we have done in third semester, a group of prime order is always cyclic. Since 2 is a prime number, therefore S3 by H will be cyclic. So now S3 by H is cyclic. But we know that S3 is not cyclic. Why? Because S3 is not even abelian. So this gives you an example of a group where a quotient group can be cyclic but G need not be cyclic. Similarly, the same example will work that if G by H is abelian, then G need not be abelian. This same example, because S3 by H is cyclic and hence it is abelian, because every cyclic group will be abelian. So it means that S3 by H is also abelian. But we know that S3 is not abelian. So therefore, it will work for that example also, where if G by H is abelian, then G need not be abelian. Hope it is clear now. In case if you have any doubts, you please let me know.